We have 100,000 drivers signing up every month, and we have at this point over 1.5 million active drivers around the world. Yeah. So it's an incredible scale to run a business at, and if that wasn't hard enough, we're also trying to change the face of logistics. I actually was supposed to have a video here, but it's a little hard. There went something wrong in the transfer, so we lost the video. But you can look it up on YouTube. We are working on self-driving cars. We made that public information a while back, and a couple of weeks ago, we started driving the public for the first time in Pittsburgh. If you are in Pittsburgh, you will see these cars coming by. You order a car from the Uber app, you may actually get one of these cars to pick you up since a couple of weeks back. There will be, there's an operator in the car with hands sort of ready to take over. And I want to bring this up as this is an excellent example of what I'm going to talk about today. This is a change of how to do things, yeah? You can spend 10 years in the lab trying to refine, every line of code in a self-driving car, or you can use machine learning and you can go practice, yeah? This car will drive for a while, then something will happen that it hasn't learned yet, yeah? And it will disengage, the operator will take over for a brief second and then re-engage the vehicle, yeah? There's a big computer in the trunk, there's these things you can see on the top, laser and cameras and other sensors, yeah? But what we're doing is that we drive people around and we will get better at it every day. Yeah? So Uber, companies like Uber, some of my previous employers and many other corporations are facing these challenges every day, which are lower prices, things like faster delivery. When I was at Amazon, we introduced 1-hour delivery. It's like kind of, I would think that 2-day delivery is a crazy idea a few years ago, yeah? 1-hour delivery, yeah? Same-day delivery for a lot of products, yeah? And we have this high customer service expectation, yeah? Amazon has 300 million customers, yeah? Uber, we have over 50 million active riders. These are huge numbers, and what you all come to expect is that we know your preferences and your habits, and we know that you're a good customer, and we don't ask any questions when you complain about a purchase or a ride, yeah? So these extremely high customer expectations are something that all corporations will have to deal with. Demand volatility, seasonal stuff, events, we have a spike in usage, we need to forecast that, it's really challenging. High number of products. I don't know the exact number, but I'm pretty sure that Amazon actually offers up more products than they have customers. Their product catalog is like huge. I've seen some crazy numbers on the internet. I'm not sure what the fact is, but it looks like a lot of products, actually many more than customers. Yeah? This is how do we manage that? Yeah? It's crazy. Yeah? Supply complexities, a lot of goods come from far away, assembled by many vendors, and more frequent shipments. Yeah? You take a ride in the morning, you take a ride for lunch, you take a ride in the afternoon, you buy something from Amazon 3 times a day. It's like that's becoming normal. Yeah? So, and in all this, we also need to think about the environment and make sure that we understand the carbon footprint of what we're doing, so that comes on top of everything else. Yeah? So overall, a very complex business situation. Yeah? We're meeting here because it's the AI Summit, and AI is really hot. But honestly, this has been underway for like many years. Yeah? A lot of companies would not exist today if it was not for machine learning. Yeah? So if we take Pandora as an example, so Pandora is pretty well known, music service. They started out as the Music Genome Project 10-15 years ago. I can't remember the exact date. Using machine learning to identify what kind, to identify new music for you that you may like based on the music you listen to. Yeah? long time ago. That's why they exist. Actually, if you look deep at their business model, it's crucial to their business model for providing free music, yeah? Because otherwise they would have to pay higher license fees if they play only what you ask for. But if they play something similar to what you really like, they pay a lower license fee, yeah? So Pandora, Amazon Echo in the press all the time, that work has been, you know, years underway, yeah? Years. Netflix has done recommendations since '97, yeah? This is like how many years, yeah? Nest, thermostats that learn from your behavior. So you tell it too cold or too warm, you don't program them, they program themselves based on your feedback, yeah? Machine learning again. And Xbox One, player matchup on Xbox Live to make sure that people, or the kids, they want to play for hours and hours and hours. They use machine learning to match up the kids in groups that play along well. And, well, Amazon, machine learning everywhere in Amazon, yeah? So let me take a quick step back, because I said this is nothing new, yeah? So the first papers on the idea of having computers doing really smart stuff is 1949, 1950. Turing is most famous for his paper, but I actually like Shannon's paper a little more. It's about a chess algorithm, and it's very interesting. If you read that paper, you would think it was written like within the last 5, 10 years. But it's from '49. And he's talking about a lot about having computer algorithms run stuff for us, very complex stuff. And he takes an example and writes about chess and how to do a chess algorithm, yeah? And he's using the Minimax algorithm, which is a very famous gaming algorithm even used today, but it's very hardwired for chess, the example that he's doing, yeah? This is a chess playing system, yeah? And it took all the time from '49 to '97 when I was at IBM, for IBM to actually build a chess computer. Special hardware, special software. Right at that point, the computer power just got there where, you know, you could use a brute force approach with some smartness in there to limit the search space, and you could beat the world champion in chess, yeah? Again, but it's very specialized, yeah? It's just for playing chess. In 2011, IBM Watson wins the Jeopardy competition. It's more standardized hardware, a lot of it, a lot of curated data, and then a Q&A algorithm. There's a very, very thought out algorithm behind it, yeah? So it can go into these questions and answers. And it was so successful that IBM figured out to use Watson as a brand very successfully. Yeah? Very recently, and this is probably why a lot of you were here, there's been this change. We have reached a point where these, the hardware, the algorithms we use become more and more generic. Yeah? And I think it was most strongly expressed in the AlphaGo example where a deep learning algorithm with standard GPU hardware. There were some special ASICs in there, but not a big deal, not that special. But this generic deep learning algorithm is tailored to the Go game and could actually beat the world champion. And that's a shift of momentum. It is not a hardwired system for just building Go, yeah? It's really actually way more based on sort of the basics in computer vision, yeah? So that is a shift. It's a shift that happened sooner than anyone thought. I don't think anyone expected a computer to beat the Go champion for another 5, 10 years at least. So this is like ahead of schedule. Yeah. If you can have a computer, if you can train a computer using somewhat standardized algorithms, standardized hardware, commodity hardware, to beat the world champion in Go, yeah? Don't you think that that system could also be trained to beat your MBA in your company, or beat your planners, and so on. So that's what I want to talk a bit about. We have seen over this period of time here this complete shift from algorithms and rule-based thinking, custom hardware software, to reinforcement learning, standardized uniform algorithms, and commodity hardware. Complete shift. Yeah? So I want to remind us that still today, 99.9% of the software around us that runs devices, that runs our businesses, is based on the idea of an all-knowing programmer who reads a spec that has all the truth in this world in it, yeah? A requirement specification. Write some code. The code takes some program data in and produce some results. And there's an amazing feedback loop, which we call, the bug system, yeah? People file bugs against it because the data coming out is not quite what we expected, and the all-knowing program will refine it, yeah? That's the feedback loop, yeah? This is like ancient stuff, yeah? This is like how Isaac Newton thought about the world, yeah? You can compute anything in this world, past, present, and future, yeah? That's what we believe programmers can do, yeah? That give them a spec, they write the code, they can go home. System done, yeah? But the world is way, 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 way more complex than that, yeah? This is like 1690s thinking, clockwork universe, yeah? Let's look at a more modern thinking about software systems, yeah? You have a learning algorithm, takes in historic data, so it takes in experience, yeah? And it builds a model for you. A model is really some code and data that can process new data of the similar form as the old data, yeah? And make predictions. I'm not saying produce results per se, yeah? It makes predictions, yeah? It basically allows you to use the learnings from the past to make predictions about the new data. So you never get anything 100% now. You move into a world that blossomed up in the 1920s, yeah? Werner Heisenberg is one of them, yeah? It's about uncertainty, it's about probabilities, it's about distributions, yeah? You never say, this customer will remain a customer forever 100%, You're never Boolean, you're never black and white any longer, yeah? You say, this customer is likely to stay with us, 80% chance they're going to stay with us for 1 month, 70% chance they're going to stay with us for 2 months. Everything becomes distributions and probabilities, and that's how we're going to run our business, yeah? Which brings me so far so good, yes? Machine learning, we're using data, we can make predictions, and we're all set, yeah? But not quite. I found some inspiration in John Boyd, who studied air combat in the Korean War, and based on his findings, that actually led to the creation of the F-16 fighter, which is a very, very different fighter plane than was originally worked upon. The fighter planes were getting bigger and bigger and more powerful and more heavy, and he said we need lighter planes, because what he realized was that the way that fighter pilots, they would win these combats was based on the OODA loop, yeah? So it's basically the pilot is observing, orienting him or herself, and then they decide to do something and they act upon it. And what he found that the faster you can do that, if you can do that a split second faster than your adversary, you're going to be more likely to win. Speed matters. Even if you observe and orient and decide the wrong thing. Yeah? If you do it very fast, you can actually spin around and fix your mistake. Yeah? Yeah? So think about that in the context of what I just talked about with machine learning. Yeah? We are to the point where we start making predictions, yeah? But we have to think about the world around us, yeah? That the world is the reality is much, much more complex than we can ever model, yeah? So we are never done. Yeah? So the moment we build a model and we make predictions on that model, we are actually now impacting the whole business environment, yeah? And we need to keep that in mind. We also need to keep in mind what I mentioned Heisenberg a moment before about looking at distributions and probabilities. And finally, we also have to look at entropy, that whenever we try to create something, it's likely to fall, you know, on the floor and smash, yeah? Nature really wants things to fall apart, yeah? So think about those three things, that reality, we can never get to a complete representation of reality. Yeah? We can never be totally exact in what we're doing. And whenever we create something, it's probably going to break. Yeah? So that's why this loop is so important. And it brings me on to a very important observation around machine learning, which is that we use historic data to build a model, and then using that model, we have to make actions, and we have to watch those actions, and we have to take the feedback loop in and rebuild our models all the time. Yeah? So that's where I'm getting to the importance of machine learning for a company like Uber. It's not something that is left in the hand of individual teams. It's something that's introduced corporate-wide. For every team to access, you need a database, you need a file system, you need a computing cluster, and you need a machine learning system. Yeah? Every team have access to machine learning. Yeah? And we have a rich set of proven algorithms, and we have scalable infrastructure, tons of servers that can run machine learning as a service for these teams. We integrate, we have a big standard database with all Uber's most common data in, so you don't have to go and dig that up yourself. Yeah? And lots of automation, and that's where we get back to the loop, which is you build models, but you actually rebuild them all the time. You rebuild your models every night to make sure that they're current and up to the latest data. And let me just very quickly cover this. I started out by saying we have these three areas of our business. And I want to focus a bit on what we call the prime area, the riders, drivers, and trips. And I want to mention our Uber Eats app. This is a team that launched recently, initially without any machine learning in there. At this point, they are using 8 machine learning models in different parts of the application, yeah, to make it better. Yeah, the estimated delivery time of your meal is no longer some average speed and the distance to the restaurant and things like that. It's actually based on 100,000 meals delivered, and we learn from the time it takes to make different kinds of meals in different kinds of restaurants. Yeah? We have multiple models. We have another model that kicks in when they actually start preparing your meal, because now we know a little more about the whole process. We have one that when the meal is picked up, we give you an adjusted time of delivery. We give you ranking, personalization and ranking of restaurants, etc. So by making machine learning readily available as a service for this team and for any other team, it allows them to use machine learning in not just one place, not just 2 places, but in this case, 8 different places in a single app. And you then expand that to all our other services and all our other efforts, really amplify sort of the need of making machine learning available broadly in the company. And I want to close out by putting a pitch in for cloud services, because there's no excuse for not getting going on this. Amazon Web Services have a machine learning service that I worked on. I also worked on the one in Microsoft, Azure Machine Learning. Google, they have one, and I always mention BigML because it's a company dedicated to run a machine learning service. And these services are excellent to get started with. There are also lots of tools available. And that was about it. Do we have Q&A or? No, we don't have Q&A. Okay, thank you very much.